For more physics-related videos, please subscribe. Welcome to Stellar Physics 4D. In this video, I will derive the Chandrasekhar limit, which is the maximum mass of a white dwarf. First, I'll briefly talk about what a white dwarf is. Then we'll come up with an equation of state for the material in a white dwarf. And then we'll find the maximum white dwarf mass, as well as the density and radius at the instability point. All of the physics in this video I already covered in previous videos, in particular Stellar Physics 3E, 3G, and 4C, where I covered binding energy, equilibrium and stability criteria, as well as thermodynamics of degenerate matter. So I would recommend you be familiar with the material in those videos before moving on to this one, because in this video I'm going to take more of a plug and chug procedure. As such, I've rated the physics in this video as intermediate. So what is a white dwarf? Recall that a star in its main sequence phase, which is most of its life, is supported against gravity by the fusion of hydrogen into helium in its core. Once the core runs out of hydrogen, the star will go on to the next nuclear burning stage, where it will fuse helium into carbon. This type of star is called a red giant. Once the core runs out of helium, the next burning phase is to fuse carbon. But this will only happen if the star is greater than about 10 solar masses. If it's smaller than that, the core will not be hot enough to fuse carbon, and nuclear fusion will stop. In this case, the star will shed its outer layers, and the core will contract until it becomes so dense that the electrons inside will become degenerate, providing what's called electron degeneracy pressure, and this will prevent the star from collapsing any further. This core is what we call a white dwarf. It will have about the mass of the Sun, and it will be mostly made up of carbon and oxygen, and possibly some heavier elements depending on the exact mass and composition of the initial star. So at this point, you may be wondering what degeneracy pressure is, or what degenerate matter is. I covered everything you need to know about degenerate matter in the previous video, Stellar Physics 4C. Qualitatively, what's important here is that it does not depend on the temperature. So it cannot be changed by changing the temperature of the material. Instead, it is provided by a quantum mechanical effect, which says that electrons do not want to be pushed close together. So if you crunch them together, there is an immense force trying to push them apart. This force, by the way, is not the electrorepulsive force due to them having the same charge. It's a completely separate quantum mechanical phenomena. Now there is a point where a white dwarf will go unstable, and that is called the Chandrasekhar limit. So let's try to find what that limit is. First, we're going to do a very quick and rough back-of-the-envelope estimate. Our equation of state is going to be relativistic and degenerate electrons. In Stellar Physics 4C, we found an expression for the number density and the energy density for relativistic degenerate matter. Now, this expression for the number density holds whether it's relativistic or not. This is the most general expression. This expression for the energy density only holds in the extreme relativistic case. To remind you what some of these variables are, G tells you how many particles you can put in a given energy state. In the case of electrons, G is going to be 2 because it has a magnetic moment that can either be pointing up or down, so that's 2 configurations for each energy state. X is what's called the relativity parameter, and it is equal to the Fermi momentum divided by the mass of the particle, in this case electron mass, divided by the speed of light. Since we're assuming relativistic electrons, we are assuming x to be much greater than 1. Lambda sub c is what's called the Compton wavelength, and this is equal to h bar divided by the mass of the particle, or the mass of the electron, times the speed of light. Since x is proportional, or x cubed is proportional to the number density, we can substitute that into this x to the 4th here to find that the energy density will roughly go as h bar c times the number density to the 4/3. The total internal energy will be the energy density times the volume. Now the number density is the number of electrons per unit volume, and the volume goes as the radius cubed. So the total internal energy will go as the number of electrons to the 4/3 divided by the radius of the white dwarf. The gravitational potential energy is just given by Newton's law of gravitation, where G is Newton's constant and m is the mass of the star. And the mass of the star will be basically the number of electrons times the mass of a proton. Summing these two types of energy gives us the total energy of the star. And what's important to notice here is that in the case of relativistic matter, both of these terms scale as 1 over r. So let's investigate this for a second. What happens if n is small? If n is small, this term will be the larger term, and the total energy will be positive, and increasing the radius will lower the energy. And since nature wants to minimize energy, this star will increase its radius, but increasing the radius means you're lowering the density, and the density is proportional to this relativity parameter cubed. So if you lower the density, you're going to lower this relativity parameter, which means eventually the electrons will become non-relativistic. And in the case of non-relativistic matter, it turns out, and it's very straightforward to show, that this term, the internal energy, will scale as 1 over r squared. So now you'll have a term proportional to 1 over r squared and a term proportional to 1 over r. As a result, there will be a radius that minimizes the energy and the star will equilibrate. So if n is small, the star will be stable. However, if n is large, then this term will dominate and the whole energy will be negative, and decreasing the radius will minimize the energy. But decreasing the radius will just increase the density, which will only make the electrons more relativistic, and there will be nothing to stop the star from collapsing. So in this case, the star will be unstable. So we can say that the instability point is when the total energy is 0. Or in other words, when the number of electrons equals the following expression. This term right here, by the way, h bar c over g, is called the Planck mass squared. So this whole thing could be written as the Planck mass cubed divided by the mass of a proton cubed. Now the critical mass, meaning the mass at which you hit this instability, will be basically the number of electrons times the mass of a proton. And if you plug in the numbers, you get about 2 solar masses. The internal energy will be roughly the number of electrons times the mass of electrons. So equating this to our expression here for the internal energy gives us this expression for the critical radius, which, if you plug in the numbers, works out to about the radius of the Earth. Okay, now that we have a rough idea of what to expect, let's do this calculation more rigorously. In stellar physics 3e and 3g, we found the general expression for the total binding energy of a star in the case of Newtonian gravity. So this is the case where gravitational fields can be well approximated with Newtonian gravity, and corrections due to general relativity are small. So just to remind you what some of these variables are, A, B, and D are constants. Rho sub c is the central density, meaning the density at the center of the star, and gamma 1 is the adiabatic index, which is related to the pressure in the following way, where K is a constant. In stellar physics 2c, I derived what the adiabatic index is for radiation pressure, meaning for relativistic material, and showed that it's equal to 4/3 plus a small correction which is proportional to this variable beta, which is just the fractional gas pressure. However, if you saw this video, you would know that I derived this for non-degenerate material, meaning I derived it in the case where both the radiation pressure and the gas pressure were determined by the temperature. So this expression for gamma 1, which I used in stellar physics 4b to find the maximum mass of a star, does not hold for a white dwarf, because a white dwarf is made up of degenerate matter. The 4/3 part, it turns out, does hold, but the correction, we're going to have to derive it ourselves. This means that we're going to have to rewrite the internal energy as a term corresponding to gamma 1 equals 4/3 plus some small correction, which we don't know what it is yet. So the total energy will have the following form. The constant A depends on the equation of state, and B and D are already known, where these numerical factors here are a result of integrating over an n equals 3 polytrope. And if you don't know what a polytrope is, then you should watch my video on polytropes, stellar physics 3b. But basically, it's just the density profile of a star. Now, these first two terms correspond to the Newtonian energy. This term, proportional to D, corresponds to the first order correction due to general relativity, and this is the correction of the internal energy. You may recall from my previous videos on energy instability that a star will go unstable when the Newtonian energy is very close to 0, meaning when this term in the parentheses is basically 0. So by setting this expression in the parentheses to 0, we get that the maximum mass will be basically A over B to the 3/2. We just have to figure out what A is now. To find A, we have to come up with an equation of state, which I've already said is going to be relativistic and degenerate electrons. If you're finding this video interesting so far, be sure to like and subscribe, and maybe share it with a few friends. We already know what the number density of electrons is for degenerate matter, and that will be related to the mass density in the following way. So here, rho is the mass density, m is the mass of a proton, a is the atomic number, meaning the average number of nucleons per nucleus, and z is the average charge of a nucleus, meaning the average number of electrons per nucleus. So rho over AMP is the number density of nuclei, and we multiply by z to get the number of electrons per nucleus. And z over a is a quantity we've encountered many times. It's often written as ye and is called the electron fraction. It's just the number of electrons per baryon, meaning the number of electrons per protons and neutrons. So now we can rewrite the relativity parameter x in terms of the density. The internal energy for relativistic degenerate matter we found in the previous video, where this term x to the -2, since x is very large, will be small, and that will correspond to our correction term to the internal energy. We'll take a look at that a little bit later. For now, we can substitute rho into x to the 4th to get that the internal energy density is equal to a constant times rho to the 4/3, and this constant is conventionally written as 3 times k. Now we have to be careful here because this expression for the energy density includes the rest mass energy. And when we talk about the internal energy, we define that excluding the rest mass energy. So we have to subtract that off. And I'm going to write it in terms of this other variable epsilon, which will be the internal energy per unit mass. So that's going to be the energy density U minus the rest mass energy of the electrons divided by the density. Rho sub E is the rest mass density of electrons, and that's just going to be the number density of electrons times the mass of an electron. So we get this final expression for the total energy per unit mass. When we integrate this term over the mass of the star, it will just come out to the number of electrons times the mass of an electron. Now this is on the one hand a small term, and on the other hand a constant term. And the equilibrium energy is found by minimizing the energy, meaning taking a derivative. Taking the derivative of a constant is 0, so this term will end up dropping out anyway, so we can just ignore it. We can now integrate epsilon over the mass of the star to find what A is for relativistic degenerate electrons. This factor, 1.76, comes from integrating over an n equals 3 polytrope. Now that we know what A is, we have everything we need to find the Chandrasekhar limit. All we have to do is plug in all the numbers. And when we do this, we get that the maximum mass of a white dwarf is about 1.4 solar masses. Notice the way I've written this. I've written this as 1.4 solar masses times 2ye squared, because we don't necessarily know what ye is. But we do know that it's going to be close to 1/2. So now the question is, if you have a white dwarf, how does it reach this maximum mass? Now, typically the way this happens is if you have 2 stars in a binary system and one of them turns into a white dwarf, matter from that star will gradually accrete onto the white dwarf until it reaches this limit, at which point something interesting happens, which we'll talk about in a little bit. Now, I don't want you to get the wrong idea here. It's very common to see this sort of artistic representation where it appears that the white dwarf is sucking material off of the surface of the star. The gravitational pull of the white dwarf onto its companion star is the same whether it is a white dwarf or a star. In fact, it's actually lower once it's a white dwarf because it's lost some of its mass. So the white dwarf does not act like this vacuum sucking off material from the star. Matter coming off of the star in the direction of the white dwarf will eventually fall into the white dwarf, and that is how it will accrete matter. Now let's take a look at the binding energy. The only thing we don't know here is what the correction of the internal energy is. The total internal energy will be the integral over the mass of this quantity epsilon. We found what the first order term is. Now we just have to integrate the second order term. But remember that x is proportional to the density to 1/3, so we can plug that in, integrate this over an n equals 3 polytrope to get that the total energy of the star will have this final form. Now that we have a complete expression for the binding energy, we can find the density at instability as well as the radius at the instability point. Remember that the equilibrium energy will be found by minimizing the energy, so that means taking a derivative with respect to the central density because that's the only thing that can vary here. And this gives us the following expression in yellow. The critical point is when the second derivative of the energy with respect to the central density evaluated at equilibrium is equal to 0. And this gives us this final condition for instability. I'm going over this fairly quickly here because we've done it numerous times in previous videos already. So if you've been watching this series, you should be getting the hang of this by now. Now all that's left to do is solve for the central density since we know the maximum mass and we know C and D. And this gives us that the central density at the critical point will be about 30 billion grams per cubic centimeter. And you can work out that 1 teaspoon of white dwarf material on Earth will weigh about 100 million kilos. So this is some truly extreme matter. For a polytrope, we have the following expression relating the average density to the central density. And for an n equals 3 polytrope, this factor is about 0.02. Now that we know the average density and the mass of the star, we can work out that the critical radius is about 1/5 the radius of the Earth. There is one more thing we need to check to make sure everything is consistent, which is that our initial assumptions are correct. So what were our initial assumptions? That the electrons are degenerate, that they're relativistic, and that Newtonian gravity is sufficient. So recall that x is the relativity parameter, so it must be much greater than 1, which is what this first expression is checking for. The degenerate condition is that the Fermi energy, which is this term here, is much greater than the temperature. Now often we say that degenerate matter is matter at 0 temperature, but it doesn't actually have to be 0 temperature. What we really mean is that the temperature is much less than the Fermi energy, so it's effectively 0. In the case of a white dwarf, the actual temperature can be really high, maybe something like 1,000,000,000 Kelvin. But as long as the Fermi energy is much higher than that, then it's effectively the same as if the temperature is 0. And this final term is checking that general relativity is negligible. I'm not going to actually check this. I would encourage you to do it for yourself, and you'll in fact see that all three of these conditions do hold. So now that we've derived all this, there's one more question to ask. Actually, two more questions to ask. First, we have to ask, well, this is a nice calculation, but does it agree with observation? Well, white dwarfs have been observed, and all of them are about the mass of the Sun and the radius of the Earth. And we haven't observed any white dwarfs greater than the Chandrasekhar limit. Well, that's not strictly true. For one thing, that limit may vary depending on YE, but it actually is possible to get white dwarfs larger than the Chandrasekhar mass if they are rotating sufficiently fast. So the rotation adds another parameter that allows you to exceed this 1.4 solar masses. But by and large, observations confirm what we've just derived here for the Chandrasekhar limit. The final question is, what happens when a star reaches the Chandrasekhar limit? And what happens is called a type 1a supernova. When a star gets near the Chandrasekhar limit, the high density and high energy triggers what's called a carbon flash, which is essentially very quick runaway carbon fusion. Now, because the star is held against gravity by electron degeneracy pressure, which does not depend on temperature, when all this energy is dumped into the star due to the carbon fusion, it cannot adjust itself to this extra energy through thermal expansion. So instead, this large amount of energy blows up the star in what's called a type 1a supernova. Now, in reality, the details of how this supernova is triggered are not very well understood, but it's something like what I just described. For sure, there is a type 1a supernova because they have been observed. So here on the left, we have a picture of a type 1a supernova going off in the outskirts of this galaxy. Now, this is not a star that is much closer to us than the galaxy. This is part of the galaxy. And you can see that this supernova is basically as bright as the center of the galaxy, if not brighter. In fact, the peak luminosity of a type 1a supernova is about 10 billion times as bright as the Sun. And the center of a galaxy will have millions, if not billions, of stars in it. This image on the right is what is left over after the type 1a supernova. So this is just the white dwarf that's been blown apart into this large cloud of material, and there is nothing left in the center. The total amount of energy released by this explosion is about the same as the total amount of energy released by the sun over its entire lifetime, which is about 10 billion years. And all of that energy is released in a period of just a few months. So this is a truly spectacular explosion, and you don't want to be next to it when it goes off. If you found this video interesting, please like and subscribe, and stay tuned for the next video where we'll derive the maximum mass of a neutron star. I've actually already covered this in a previous video, Stellar Physics 3D, but in this next video we're going to look at it from a different point of view, which is more or less akin to what we did in this video. So be sure to hit the bell to be notified when this video comes out.